Hello everyone. In the last class we have studied unit load method. Okay, unit load method, and we have covered topics related to beams. So in the today's chapter we will cover unit load method, unit load method, and we'll see how to use this unit load method in frames. So basically, what is a frame structure? Frame is a simple building structure. The supports may be hinged or pinned or any other supports that we get acquainted in civil engineering. So this is a basic frame structure. So we will see how to use this unit load method in analyzing this deflection and slope in frames. Okay, so what was the basic formula that we used earlier? The basic formula was, if we have to find deflection, then we will have mm dx by ei, suitable integration. This was for deflection, and if we had to use slopes, then it was capital M dx by ei, same formula, but in case we have to find deflection, we apply unit load, and in case we have to find the slope, we apply unit moment. This was the only difference. So let's start with a question. So if we are given with a frame like a structure like this, suppose this point is a load is acting over here, this point is b, this c, another load is acting over here, point D, and this is the free end, point E. So this is a frame structure. This is 2 meters, this is 1.5 meters, this is 1.5 meters. Okay, so this is the dimension of the frame, and the load which is acting is, here it is 10 kilonewton load, and here the load acting is 20 kilonewton load. Okay, so we have to find deflection. So deflection at free end. What is the value of deflection at free end? Okay, so we know that if a load is acting on this frame like this, so we will have deflection. The frame will try to bend like, the frame will bend in this manner. Okay, so basically the frame is undergoing two kinds of deflection. One is a horizontal deflection, which is going in this direction, and another is a vertical deflection. So we have to determine horizontal value of deflection and vertical value of deflection. Okay, so we will see them one by one. Okay, so let's start. So we are given with a frame. This was the frame. This was 10 kilonewton, this was 20 kilonewton, 1.5 meters, 1.5 meters, this is 2 meters, and this is 2 meters. Okay, this was point A, B, C, D, and this was point E. So in the first case we will analyze what is the value of horizontal deflection. So as we can recall from the earlier concepts that we used to determine two kinds of moments, capital M and a small m. What was this capital M and what was this small m? This capital M was moment due to the actual loads which are acting on the frame, and this small m is the value when all the loads in the frame are removed and a unit load is placed at the concerned point. Okay, so the value of m will be simply the value of moment that are being induced in the frame by this 20 kilonewton load, this 20 kilonewton load, and this 10 kilonewton load, and the various reactions that are going to act on the supports. And this value of a small m is used when all the loads are removed. Okay, and a unit load of 1 kilonewton is placed at the point where deflection is to be determined. Okay, so let's start this value. So we will analyze point wise so that our calculation will get easier. Okay, so we will first analyze the points part ED, then we will analyze the part DC, then we get to analyze the part CB, then part BA. We will try to find the value of capital M and the value of small m separately in these two parts. Okay, this value of capital M and value of small m. So let's start. So for part ED, we can see that frame is in this manner. This was point E, this was point D, this was point B, C, this was point A. Okay, so in part DE, no load is acting, so the value of capital M is 0. Okay, since no load is acting on this point DE. Similarly for point DC, at any point X, what is the value of moment? This load is 20 kilonewton. So if we go from point E, D, C, B, we cover in this manner. So we can see that in part DC, at any distance X from D, the value of capital M will be 20 into X. Okay, it is actually clockwise. So let us assume clockwise as positive. So the value of capital M is 20x. Okay, similarly in part DC, DC we have covered. So part CB, what's the value of moment in part CB? CB is actually moment due to this 20 kilonewton load. Okay, so what is the value of this 20, and this moment is passing at a constant distance from this horizontal member of the frame. Okay, and what is the distance? It is 1.5 meters. So what is the value of moment? It is actually 1.5 into 20, which gives 30. Okay, so it is 30 in part CB. And what will be the value of moment in part BA? Is actually, this is 10 kilonewton load, so the moment in part BA is 30. This is acting clockwise and this is acting clockwise, so it will be 30 plus 10 into X. So this is the value of capital M in different parts of the member. Now we will determine what is the value of small m. Okay, so let's determine the value of a small m. So for a small m, we remove all the loads that were acting on the frame and place a unit load at the point where deflection should be determined. Okay, so this was point A, this was point B, this was point C, point D, and this free end was point E, and this is 1 kilonewton. So what is the value of a small m in ED? It is actually 1 into X, simply X. What is the value of small m? This is actually capital M. Okay, and this is small m, remember that. So in AD it is X. What is the value of moment in part DC? It is simply 1 into, this was 1.5 meters, so it is 1 into X plus 1.5. okay, X plus 1.5 meters. Okay, it is acting clockwise, so let's take it positive. What is the value of moment in part CB? CB, this part, actually this load is acting over here and it is acting at a constant distance from part ABC. So the value of moment will be a constant one. So what is the value of moment? It is actually 1 into this 1.5 plus 1.5 is 3. So the value of moment is 3, small m. Okay, and what is the value of small m in part BA? It is also 3 because the distance is same. This distance is 1.5 plus 1.5, 3 meters. So it is actually also 3 meters. So what do we get? In part ED, we get the value of capital M as 0 and small m as x. In part DC, we get the value as 20x and the value of small m is 1.5 plus x. Okay, in part CB, capital M is sorry, not minus, it was actually plus. We can take plus or minus according to the sign convention. We can assume on our own. If we assume clockwise as negative, then we can carry out the calculations using clockwise negative, and we can also assume anti-clockwise negative. So whatever you assume, you just proceed your calculations assuming that thing only. Okay, so we have assumed it as a positive one, so it is a plus 30. And what is the value of small m? Small m is plus 3. And sorry, in part BA, value of capital M is 30 plus 10x, and the value of small m is 3. So we have obtained the results of capital M and small m. You can note down these values in your notebook. Okay, so we can carry out the calculations further. So to determine the deflections, what we had the formula delta. We are determining actually vertical deflection. Okay, what we have assumed that the load is acting in a vertically downward direction. So what will be the shape of the frame? Shape of the frame will be this one, this vertical deflection. We are interested in this vertical deflection, so we will write here what is the value of this vertical deflection. It was m small m dx upon ei and limit of integrations. Okay, so what will be the limit of integrations? Limit of integrations will be from E to D. It is 1.5 meters. So for ED, the limit will be 1.5 meters. For DC, it will be 1.5 meters. For CB, what is the length of CB? It's actually CB, and this one is A. So CB, it is actually 2 meters, and this is 2 meters. So for CB, the value limit is 2 meters, and for BA, it will be 2 meters. So let's carry out with these calculations. Okay, so if we are writing the equations for part ED, then we have delta V equal to mm dx by ei. So what is the value for ED? What is mm dx by ei for part ED plus mm dx by ei integration for part DC and so on. Okay, so let's put on the values of m and small m as from the calculations we have derived earlier. So For part ED, the value of m is 0, so it is 0, and small m is, the value of small m is minus x by EI, limit 0 to 1.5. okay, plus for part DC, value of capital M is 20x and the value of small m is 1.5 plus x dx upon EI 0 to 1.5. This is for part DC. For part CB, it will be capital M is 30, small m is 3 upon into dx by EI. This limit is 0 to 2 because length of the part CB is 2 meters. okay, and again for part BA, it is 30 plus 10x into 3 into dx by EI. This also is law of length 0 to 2 meters. So we can see that this part of integration was for ED, okay, this integration was for DC, this part of integration was for CB, and this part of integration was for BA. We can separately integrate them and then add the values to come to get the final value of delta V. okay, so we can see that EI is constant in all the terms, so we can take this EI to left hand side and we will get the expression like EI delta V equal to those expressions. okay, so ignoring the term of ED, we will be getting only term of DC plus CB plus BA. okay, so if we carry on the calculations, we will get for part DC, it will be 20x into 20x into 1.5 plus x sorry 1.5 plus x dx integration 0 to 1.5. okay, plus for part CB, it is 30 into 3 dx by EI integration from 0 to 2, and for part BA it will be 30 plus 10x into 3 dx by EI. Limit of integration it will be from 0 to 2. So this is the expression. So we will solve separately this term and this term. okay, so we will obtain the final results as EI delta V will be equal to 40 476.25. okay, so what will be the value of delta V? Delta V will be 476.25 by EI. okay, this is the answer. So this was the first part that we have covered. okay, you can go through the integration. It will be a simple integration that we have studied in 11th or 12th class, so there is no need to show you the integration process. okay, so I have shown you the methods. So this is the value of deflection in delta in vertical direction. okay, so let's come and deal with the second part of the question. What does the second part asks? Second part of the question asks what is the value of deflection in horizontal direction. okay, so what will we do? This will be a simple frame, and this frame bends in direction along this manner. So here it is asking to find the value of this deflection. So it is in horizontal direction, so the deflection will be represented by delta H. So what will we do? We will simply apply a unit load along this direction, in the direction where the displacement or deflection is to be determined. okay, in the initial case we have to determine the vertical deflection. So we have applied the unit load at this point in vertically downward direction, but in this case we have to determine horizontal deflection. So we will apply the unit load in horizontal direction. okay, is it clear? In whatever the direction the question is asked to determine the deflection, we will apply the unit load in that direction only. okay, so I think it is clear. So in this second part of the question we will apply 1 kilonewton of horizontal load. So again we will carry the same part. It was E, it was point D, it was point C, it was point B, and it was point A. okay, so we will obtain capital M and a small m for point ED. In this case ED, DC, CB and BA. okay, so we have already determined the value of capital M in all those parts, so I am just writing the values of those here. So in ED the value of capital M was 0. In DC capital M was 20x. In CB the value of capital M was plus 30, and in BA the value of capital M was 30 plus 10x. okay, now we will find the value of small m when the load is applied and the free end in horizontal direction. So this is the frame. Let us draw the frame. This is the frame. We have applied the load in horizontal direction, and we will determine the value of small m in each and every part. So since the load is passing along the horizontal member of the frame, so the moment in this ED part and in this DC part will be 0, because 1 kilonewton is passing along this direction. So the distance of this force from every point on this member is actually 0. So this 1 kilonewton horizontal force will create a 0 moment in this member of the frame. So here it is 0, here it is 0, and this 1 kilonewton force will create a moment of simple in CB. It was C, it was point B, it was point A. So in CB the moment created is simply 1 into x. Okay, so it is 1 into x, simple x, and in part BA it will be 1 into this value is 2 meters, and the distance taken from point B. Let me make the diagram clear. Okay, this value is x, and if this is the frame, 1 kilonewton is acting in this direction. This is point C, this is point B, and this is point A. So this is 2 meters, and we take x from over here, it is x meters. So this 1 kilonewton force will impose a moment of 1 into 2 plus x. Okay, this value is 2 and this value is x, so it will be actually moment is 1 into x plus 2 meters. Okay, so we have obtained the value of capital M and we have obtained the value of small m. So let's write down in a table in a proper manner. Okay, so for ED, capital M was 0, small m was 0. For DC, capital M was 0, small m was, no, sorry, capital M was, it had some value actually. For ED, capital M was 0, small m was 0. For DC, the value of capital M was, what is the value of capital M? It was actually, let us draw the figure first. It was 20, so it was simply 20 into x. Okay, for CB it was 30, and for BA it was 30 plus 10x. What was the value of small m calculated? The value of small m calculated was actually 0 for ED, 0 for DC, and CB, what was the value? It was simply x, and it was x plus 2. So this is the value obtained. Now we will put the values in the equation of unit load expression. What was the expression? Now we are deriving the horizontal displacement, so we will write delta H equal to mm dx by EI integration. So we will move this EI towards here, we will obtain EI delta H will be equal to mm dx by EI to various limits. Okay, so for ED the limit will be, if this is the frame, this was point E, this was point D, this was point C, this was point B, this was point A. Okay. Sorry. So for AD it will be from 0 to 1.5, for DC it will be from 0 to 1.5, for CB it will be 2 meters, 0 to 2 meters, and for BA it will be 0 to 2 meters. Okay, so we will write this expression in a separate manner. So let's write the expression. So we will have EI delta H equal to, for AD, actually the for AD part, AD plus DC plus CB plus BA. The value of capital M and small m was 0, so this AD part we can ignore it to 0, and the value of a small m for this DC part was also 0, so we can ignore this value also. Okay, so we are remained with only two parts, which is CB and BA. So we will write the expression only for CB and BA. So what was the value of capital M for CB? The value of capital M for CB was 30. And what is the value of a small m? It was simply x dx, integration from 0 to 2, plus for BA integral will be from 0 to 2. What is the value of capital M? It was 30 plus 10x. 30 plus 10x. And what is the value of a small m? Small m was x plus 2, or 2 plus x dx. Okay, limit is from 0 to 2. So if we go on integrating this term and this term, we will obtain the value of EI delta H as 306.66. Okay, this is the value that comes after integrating these and these terms. Okay, so what is the value of delta H? Delta H comes out to be 306.66 by EI. Okay, so we have solved the value of deflections, the two types of deflections. We had this frame. Okay, we had to determine the value of deflection, this vertical deflection and this horizontal deflection, using unit load method. So we have seen that how to apply this equation dx by EI in frames. So this formula is actually applicable in beams, and it can also be applied in frames. Okay, this formula. But in case of truss, we will not use this formula. Truss has its own kind of formula. Okay, so we will see in the next few lectures that how to use this unit load method in truss. Okay, so that's all for now.